সুপর্ণকে বলে GMSM এতে জয়েন করাতে।
GMSM এ লিংকটা দিতে
গ্রুপে নয়, এতে জয়েন করাতে।
আমি জয়েন করাতে
PC Canada, Scientific Canada, as a research scientist where he is presently working. Today, he's going to talk about the basic working principle and application of organic electronics device and energy storage device. Now, I would request to our respected inaugurations program.
Many thanks, Suparna, for your
Thanks.
very fine introductory speech. Good morning, dear students, respected colleagues, and participants. On behalf of our Gaurmon Sachin Mandal Mahavidyalaya family, I do convey our heartfelt good wishes to all of you. And I would like to welcome you all to this international seminar being conducted over the internet by the Department of Environmental Science of our prestigious institution. Such high standard of academic program, you may call it a pleasure talking. If you like to get familiar with the expression as is used by our honored resource person, Dr. Anindo Ganguly, in his acceptance letter, is arranged in order to get our students encouraged and motivated. Dr. Anindo Ganguly, our distinguished speaker in the webinar, is an eminent scholar and research chemist of TC Scientific Incorporate, Edmonton, Canada. We are now at the eastern side, and you are at the western, of course. You are on the northern side of the globe. Here it's 11:40 a.m. So good morning to all our students and colleagues and participants. But your time is 2:20 a.m.
Right.
Though exactly it's not midnight, but it's deep night for you. So good night, Dr. Anindo Ganguly. How are you?
Yeah, I'm doing well.
The pleasure of your night sleeping is gone.
No, it's okay.
But positively, you are awakened in your spirit, in your mind, and in your love for our dear students of the college. Would you believe this talk of yours surely is going to be the pleasure talk? We are happy and proud to extend our warm welcome to you. We would like to thank you, Dr. Ganguly, for your kindness and courtesy to be the distinguished speaker in this webinar. Dr. Ganguly will deliver his big talk on introduction to organic electronics and energy storage devices. Organic electronics. I am a teacher in philosophy and principal of
No
this college.
problem.
and you are from science. Organic, your subject is, your topic of discussion is organic electronics. And it is a field of material science
Right.
dealing with design, synthesis, characterization, and application of organic small molecules
Right.
or polymers that show unique electronic properties such as conductivity. And organic electronic materials are used to convert light into electricity in solar panels. Very
Right.
fantastic, outstanding topic. Our dear students, our dear students, for whom mainly this talk is arranged, I hope they positively will be benefited from this discussion. And indeed, we like to get them motivated. We hope they will learn from this talk how to think, how to study, and how to see big dreams for a better life. In short, we like to motivate our students for big thinking, for their better future, for their better career. We are thankful to our president of the college, Sri Joydev Haldar. He is president of the governing body of this prestigious institution. On all occasions, we are accustomed to get good support, advice, and guidance from him. So, many, many thanks to him. Professor Ranjini Guho of the Department of History and IQAC coordinator. Professor Anupama Moitro, yeah, hello, Anupama madam. Anupama Moitro, she is academic in charge of our institution. Sri Deprasad Mondol is secretary of the Teachers Council of this institution, and Professor Piali Das, NAC coordinator of the college. All have wonderful enthusiasm and good support for arrangement of this webinar. I thank them very sincerely. And our respected teachers, Orundhati and Suparna Ganguly, Pradut Mondol, Sushama, and Suparna Ganguly, all our respected teachers of the Department of Environmental Science. They are very dedicated, they are very sincere, and they always used to take care of the students of their department and for their support and cooperation. It is mainly for the students we had arranged this program, academic program. We equally do believe that our other teachers and researchers and participants, of course, at home and abroad, having interest in this topic will be benefited from their participation in this webinar. I wouldn't like to take much time because our distinguished eminent speaker is ready and yes, come for our dear students from his deep sleep with his awakened mind and spirit. I would just request our Suparna Ganguly to proceed with the big request to our resource person. Once again, many thanks to all. Have a good day.
sir, it will be impossible to conduct this webinar without your enormous support. Now I would request to our resource person, Dr. Ananda Ganguly sir, to deliver his speech. We all are eagerly looking forward to your speech.
Okay, so everyone can hear me, right? Suparna, can you hear me?
Yes, yes, yes.
Okay, so let me present my slide. So can you see my slide?
Yeah.
Okay.
Yeah.
Okay. Yeah.
Yes, it's visible.
Okay. Yeah.
Go on. Yes.
So yeah, as you can see that first of all, thanks to Principal Sir for such a nice introduction. Thanks to Suparna and Sushama ma'am for all the nice words and the introductory note. So as you can see that my talk title is Introduction to Organic Electronics and Energy Storage Devices. So when first Suparna told me or requested me to prepare a talk, I was a bit clueless because this is a complicated topic, and at a glance, if I present these to a bunch of undergrad students, they will be scared to see the title, like what is this, and like will they really understand anything? Or so I was scared at the beginning. Okay, so definitely I can make a presentation which is tangible, which is understandable, and instead of presenting complicated technical data, I can introduce all the students to this field and the devices, because there are industries growing on those techniques. So if they are inspired, it can become their profession in future. So that's the motivation behind this talk. So I would mention about my research work a little bit, but my main goal today is to introduce these devices to the students. And if they have any questions, I'll try to answer my best. If not, I'll leave my email ID over here, and then they can be in touch in future as well if they are interested and want to pursue any sort of study or profession in this field. So with that, having said that, let me get started. So what is really organic electronics? What does it mean? So organic electronics means electronic devices run by organic semiconductors. Now, if I tell you like what is the most commercialized version of it, like if you go to a shop, electronic shop, what can you see that is made of organic semiconductors? So suppose if you go to buy a television, and then you see that it's a Samsung or LG TV and it's written OLED, that means it's made of the screen, the display is made of organic light emitting diode. So that's a electronic device, organic semiconductor, and that's the screen is made of that device. And similarly, if you see advertisement of any phone which says the phone screen or phone display is made of OLED, that means the screen is made of organic semiconductors. So that's to give an idea like where we can expect to see them and what does it really mean. Now, when I say organic semiconductors, two things comes to mind first. First is that what is really semiconductors? And after that, what does it mean by organic semiconductors? So let me try to explain like what a semiconductor is. So if we are talking about the charge flow of electrons whenever you're talking about charge conduction, right? So thinking about charge conductions, in general, there can be three types of materials. First of all, conductors, which can conduct charges. If you think of the most common example, that's metal. So I have image of copper wire. So you can always see, if you just look back on your wall, you will see the wiring of the copper wire. It is conducting your electricity to your house. And then the next thing is insulator. Maybe the common example is glass. That means which cannot conduct any electricity, which cannot conduct any charges. Then the last last type of material is semiconductors. So it says semi means half, conductors. That means it falls between conductors and insulators. So the common example might be silicon. I'm hoping everybody has heard of silicon. There is also germanium. So they behave as semiconductors. Now, what does it really mean by semiconductors? So again, its primary function is flow of charges. That means flow of electrons, you can say, or flow of positive charges through that device. Now, semiconductors conduct charges under certain conditions. So that's the key point. So for metals, you don't need any particular conditions. It always have free electrons and it will always conduct charges. Glass, no matter what you do, it will never conduct electricity. But semiconductors conduct charges under certain conditions. That means we can turn it on and we can turn it off. So that means it can work as a switch for the charge flow, for the electrical conductivity. So where do we see the semiconductors? We see it everywhere these days. If you have a vehicle, if you have a car, you have multiple semiconductors in that car circuit. If you have a computer, if you are the computer you are using right now to connect to this talk, it has a bunch of semiconductors. If you have a memory device in your phone, in your laptop, it has a number of semiconductors devices. Now, from here, how does it behave as a switch? As I said, it under certain conditions only it will conduct charges. Then how does it behave as a switch? So let me try to explain it from the most simplest way, in a most simple way. So we have all studied class 12 science, right? So if you go back to the Bohr model, where we know the structure of atoms. So suppose we have on the left-hand side, we have a structure of atoms, and then we have a nucleus at the center, and then around the nucleus, we have cells of electrons. And as we go towards outer side, the number of cell increases. So suppose the atom has 6 electrons. So the first cell has 2 electrons, the next cell has another 2. And then the third cell has another 2. And then we have also remaining orbital, like that, remaining empty orbital. So as we go, the cell which is the most outer cell, that's very important in case of any chemical atom. So this is called valence cell. When a reaction happens, these are the electrons takes place in the reactions. So in case of semiconductors, these or any conductor, the most outer cell where it has electrons, and the next empty cell, next empty orbital, those two particular orbitals are very crucial. So if we look on an energy scale, suppose the energy of the orbitals are increasing. So this is the topmost orbital which has electrons, and the next empty one is this one. So that energy difference is very crucial in case of any semiconductor. So now I'm talking about a single atom here. So semiconductor is a property of solids. So if we put all these atoms together, hundreds or thousands or millions of atoms together to make a solids, then these orbitals actually come closer and they overlap. So overlap, and then the valence cell electron, that remember that the most outer cell which has electron, it forms a valence band. So suppose I'm showing that band by this blue box here, and then the just exactly next empty orbital, they also come together and they also form an empty band. It's called conduction band. So that's always empty. So now for charge to flow, in any conductor, in any material, the electron has to rise from this valence band to conduction band. When it rises to conduction band, the electron becomes free. And when it is free, it can flow through any system and we can generate electricity or power. So for metal, there is no energy band gap. So these two, the valence band and conduction bands, they basically overlap with each other. So that means we have no barrier to push the electron from valence band to electron conduction band. So it can easily move charges. So that's why metal doesn't really need certain condition. It has always free electron. It can always conduct charges. Now, if we look into the insulator on the right-hand side, this band gap is so high. It doesn't matter whatever energy you are providing from outside. It can be light energy, it can be electrical energy. It doesn't matter. It is so high, you cannot provide enough energy for electron from jump to valence band to conduction band. So that's why we cannot get any free electron insulator like glass. So it will never conduct electricity. So now the last thing is semiconductor. Semiconductor has this energy band gap in a range where if I provide energy from outside, an electron can absorb energy and it can rise from valence band to conduction band. That means when I'm providing energy, it's a condition, right? So suppose I have light on it, and then after the addition of certain amount of light, an electron can go from valence band to conduction band, and then we can take that electron and freely move somewhere and do something. So that's the concept of semiconductor. So that energy band gap is a characteristics of a particular semiconductors. It cannot be, it is like, it's a characteristic properties. Each semiconductor has unique band gap, and then we can provide that band gap energy to raise one electron or multiple electrons from valence band to conduction band to make a charge flow. So that means when I provide that certain conditions, it will work. When I stop that certain condition, it will not work. So basically it's a switch. I hope it explains why it works as a switch. Now let me move forward. So now there are in general two type of semiconductors we deal with. One is called p-type and another is called n-type. So what does it really mean by p-type? P-type means we can dope. Dope means we can add impurities to semiconductors in a certain way that the charge flow is dominated by positive charge, or we can call it hole. Like in semiconductor science, we call it flow of holes. So that means it's a p-type semiconductors. So charge flow is dominated by positive charge. Similarly, if we can dope a semiconductor in a way that the charge flow will be dominated by electrons or negative charge, so then we can call it n-type semiconductor. So p basically means positive charge carrier, n basically means negative charge carrier. That's all it means. So now, so we have learned about semiconductors, we have learned about two types. Now next, just learn about one single device. So still I haven't talked about organic electronic devices. I'm still on semiconductors. So the most common thing that probably you have seen outside is the silicon solar cell, a blue panel. Maybe you have seen on a rooftop, maybe you have seen by roadsides. You have seen those blue panels, and then it's facing towards sun, it's harvesting solar energies. So let's see how it works in a simpler way. It's not complicated. So I have made a cartoon how to explain how it works. So suppose like in like how does the device looks like? So basically in a silicon solar cells we have one n-type silicon layer, then one p-type silicon layers. So p will basically conduct positive charge, n will basically conduct negative charge. And then we have two metal electrodes, one at the bottom, one at the top. That's the simplest version. So suppose we are shining light on a silicon solar cell. And then what happens? So we have shine lights on silicon solar cell. So on the p-type, suppose there is an electron which gets excited because we are shining energy, right? We are switching on that conditions. So an electron can absorb energy and can jump from valence band to conduction band. So that's what happens when light comes on and hit the solar cell. And then what is next? So next is, so you can see the N silicon, the N-type silicon, there is like the conduction band is a little bit lower on energy scale. So that means it has a lower energy. So any electron will always try to stabilize itself by releasing energy. That's how nature made them. So once it's raised, it will find out that, okay, there is another orbital which has a little bit lower energy, so I can release some energy and get more stabilized. So then it will transfer that electron to the conduction band of N-type silicon. And then if we connect the two electrodes, the metal 1 and metal 2, remember, on the top and the bottom, so then that electron will flow through the circuit. And once it's flowed through the circuit, that generates power. So basically it's Ohm's law, power is equal to current into voltage. So definitely you can see there is a two different electrodes. Two different electrode means they will have different voltages. So that voltage difference, and then whenever the electron is flowing through the circuit, there is a charge flow. That means there is a generation of current. So basically the current and voltage will give you the amount of power. So to draw the power, we have to add a load. I have not shown it. I have not made it complicated. So to draw the power, we have to add a load, maybe something, a bulb, or maybe a computer or anything, and then we can extract power from it. Okay, so that's the basic concept of silicon solar cell and how it works. So now we have learned about semiconductors, we have learned about inorganic silicon semiconductors, and we have learned how solar cell in general works, whatever we have seen in our daily life. Now let me talk about organic semiconductors. So now we know what semiconductors is. Now if there is a carbon-based molecules or polymers behave as semiconductors in its solid state, then we call it organic semiconductors. It's as simple as that. Of organic semiconductors that were like early days, those are introduced for solar cells. So since I'm talking about semiconductors, organic semiconductors, let me tell you why are they important? Why do we really care about them? What is good about them? So first of all, so remember, as I said, you have seen maybe a solar cell like silicon solar cell on the rooftop, maybe a hard blue panel and taking a lot of space, right? So that's where the beauty of organic solar cell is, that organic materials are soft and they can be installed, they can be fabricated on plastic surface. So plastic surface is pliable. We can bend it. It's flexible. So when we can print it on plastic surfaces, that means we can just print it like newspaper. So the processing of organic solar cells is very cost effective and it's very fast. So within 10 minutes, we can print a solar panel of organic solar panel of a size of football ground. It is that fast. It's just like our newspaper. You can imagine, we have seen the newspaper printing out from the machine, right? How fast it is. So that's the one advantage. That means less time, means less energy, and then less money. So we don't need to spend that much money to process, to fabricate organic solar cells. Next is organic solar cells, or maybe organic like other devices as well. I'm talking about in general organic semiconductors so far. Since I said it can be fabricated on plastic, that means it's lightweight, right? Plastics are lightweight and it's flexible. So think about it. Suppose you want to have a car and you want the rooftop of the car laminated with solar cell. So you always want to have a light solar cell, because if you put more weight, you have to spend more petrol because you are always carrying that solar cell, right? So that means what I'm trying to say, suppose if I have a solar panel on my car rooftop, it can absorb solar light during the day, and I can use that energy, the solar energy produced, to drive my car. So for all of these kind of applications, I need lightweight solar cells. So organic solar cell can serve that purpose. The next point is flexible. That's very important. So suppose you all have cell phones, right? So suppose you have a backpack and you want to laminate the outer surface of your backpack with a solar panel. Now, we cannot do it with silicon solar panel because it's hard. It cannot be laminated on a flexible surface. But for organic solar cell, it can be laminated on backpack. It can be laminated on your clothes, on your fabrics. Even it can be laminated on your glass walls. So suppose I have a building and I want to, like, instead of coloring the building outside walls, I want to laminate with organic solar cells, because also organic solar cell can be colorful. So inorganic solar cells, silicon solar cells, you have seen they come only in blue colors. So I'm showing the blue color also here for organic solar cell, but it can be green, it can be red, it can also be colorless. So when it is colorless, think about the advantage. We can put it on our window glass, right? So that means, suppose the sun is coming through our window, so during that passage, my solar cell on the window can absorb solar light, and it can convert that into electricity, which I can use at my home. So that's the advantage. And also the large area application, as I said, like in Germany, it has been done so far. One large football ground, the galleries all are covered with solar panels, like organic solar cells. And it's basically the electricity is like the power run by that solar cells over there. So that's the advantages of, I just talked mostly about solar cells, but there are other devices which I would mention at the end. So for today, I'm just focusing on solar cells because I did not want to make it again complicated. I just chose one devices. Now how does a organic solar cell look like? So as I said, it has different layers like silicon solar cells. So at the middle, we have seen we can see there is an active layer which is made of the organic semiconductors. So then we have one electrode, that is aluminum on the top, and then another electrode, ITO, indium tin oxide, at the bottom. So basically, you can imagine the similar sandwich structure I have shown for silicon solar cells. Now there are two other layers, which is LIF, lithium fluoride, which you can say electron transport layer, and then another is PSS, which is hole transport layer. So that means, so now what are the importance of these layers? So these layers are not very important for us to understand now, but I'm just mentioning. So once this active layer absorbs solar light and produce charges, they need to find out the electrode. So they need to channel through this layer to electrode. So when I have an electron transport layer, it can easily collect the electron and send it to that electrode. It helps to collect the electron. Similarly, PSS is a hole transport layer. So it helps to collect the positive charges. So that's where the purpose is for those two other remaining, like the extra layers. So now that's the common architecture of organic solar cells. And now how it works again. So again, active layer has two types of semiconductors. It's p-type and n-type. So let me tell you one thing. I have, for your easy understanding, I have shown the silicon solar cell first, but it's a bit different. Like organic semiconductors, still it has p-type and n-types, but you don't need doping, or you don't need to add any impurities to make it p-type, n-type. We can design the structure in a different way so it can behave as p-type and n-type. So there is a bit of difference of organic semiconductors and inorganic semiconductors, just for you to know. I'm not going into details. So now how it works again. So suppose I have, again, what does it really mean by HOMO and LUMO? That basically means what I have shown, valence band, the most outer cell which has electron, that is called as HOMO. In case of organic solar cells, and the exactly next empty orbital is called LUMO. That means HOMO means highest occupied molecular orbital, and LUMO means lowest unoccupied molecular orbital. So what happens when light hits the solar cell? Again, it generates a charge pair. So electron means negative charge, hole means positive charge. So it get excited, the electron get excited. Again, you can see there is a energy offset between these two LUMO, or two, you can, for your understanding, you can say two conduction bands. So electron jumps from one LUMO to the next LUMO of n type, and then it can easily go through those charge transport layer and finally reach electrode. And if we connect the electrode from the outside, again the electron will run through that electrode and definitely will generate power. So that's the basic principle of organic solar cell again. And now again, it's a for organic solar cells, it's a common p-type semiconductor that has been used. It has shows like around 5% efficiency. Efficiency is the primary merit of a solar cell. That's how basically it means how much light it is absorbing and how much current or power it is producing. It's a ratio of those two. So that gives an idea that how efficient it is. So from there, what I did during my PhD, so basically I made a bunch of organic semiconductors. So these are p-type materials. So again, I'm not going into details how I made them and like their properties. So I'm just showing you some of my work. So basically, it's a derivative of iso-indigo. So there is a relation of indigo with our history, because we all know about indigo nil vidroho, that means indigo revolt. So it's an isomer. So today's all the jeans maybe the students are wearing or any of you are wearing, if it is a denim jeans, if it's a blue, it's colored by indigo, the dye. And this molecule, it's a little bit of little bit different than molecule. It's an isomer, we call. So I took this dye and try to use them in conductors. So I made all of these molecules, and I did some angels. Again, I use indigo and iso-indigo derivatives. So all of these are polymer. You can see I have this is not a single molecule. It has N, means there are a number of units that are connected to each other. You can think of plastic or polyethylene. So I made these three type of N-type materials as well, and then I studied them. So details on how to explain this data or give an idea. On the left, I have visible spectroscopy. It gives an idea. Semiconductors are cells, right? So that means it has to absorb light. It has to absorb light very well. Otherwise, it cannot work, right? So that's the technique that gives you an idea how much. Side, I have shown you the electrochemical data. So that means it's basically cyclic voltammetry data. So it gives an idea. I have shown you about the band gap, right? Band gap of a semiconductors. It's a unique property of semiconductors, right? So when I